With that, let's welcome David.
Thank you, Satinder. It's really a great pleasure to be here. So today I'm going to talk about AlphaZero, which is Deepmind's latest deep reinforcement learning architecture. It's actually achieved superhuman level in many games now, without human knowledge beyond the game rules. And this is joint work with many great collaborators at Deepmind that are listed at the bottom there. So I'm going to start with the game of Go, which is the oldest and most deeply studied game in human history. It's around 3,000 years old, and it's played currently by around 40 million active players around the world. So in some sense, you can think that it represents the pinnacle of human knowledge in any game. It's been studied by professional players who've developed this enormous pyramid of knowledge over many, many years. And so in some sense, it makes a perfect testbed to really understand how far we've come with our machine learning and artificial intelligence-based approaches relative to the best of human knowledge. It's also been viewed as a grand challenge to artificial intelligence. And this is largely due to the enormous size of the state space. So this oft-cited figure of around 10 to the 170 states in the game of Go make it very challenging for traditional search-based methods. So I'm just going to start by visualizing what that search space looks like. So in the game of Go, there's a branching factor of around, say, 200. And at each one of these positions that you're in, you have 200 possible actions that could be taken. And leading to new positions where, again, there's 200 more decisions that could be made, and so forth. And this actually lasts for several hundred moves. And so we actually have something like 200 to the power of 200 possible sequences in the game tree. And so this really renders the game of Go completely intractable to traditional search methods, and has meant that something new was required to make progress. So I'm going to start by talking about the original version of AlphaGo, which became the first computer program to defeat a human professional player, and then the first program to defeat a human world champion. So at the heart of AlphaGo are two convolutional neural networks that represent knowledge about the game of Go. So the first of these is the policy network, which is illustrated here. So the policy network, which we're denoting by this green P in this talk, represents AlphaGo's recommendations of moves to play. So in each position, it's fed in a representation of the position as different planes representing the board, such as where the black stones are, where the white stones are, where the empty intersections are. And this is fed through many convolutional layers to process this position into increasingly abstract features representing knowledge about the game of Go. And finally, this is brought together into a policy distribution over moves that actually recommends which moves to play. So in this situation, for example, we can see that that toolbar is suggesting that in this particular position, one particular move is considered to be a very good move and is suggested and recommended with high probability, whereas many of the other moves, such as playing in the corner, would have near zero probability. And so this is how AlphaGo recommends which moves to play. The second neural network in AlphaGo is called the value network, and this represents AlphaGo's positional evaluation knowledge. And essentially what it does is it predicts the winner of the game. So again, it takes a representation of the position of the game of Go as an input. It processes it through a convolutional network. But this time, it kind of takes that and it aggregates all of that knowledge together in a final layer that combines this together into a single scalar value between -1 and +1, where +1 means a prediction of certain win for AlphaGo, and -1 means a prediction of certain loss. So these neural networks are trained in AlphaGo, and I'm going to represent a slightly simplified representation here of the training pipeline in AlphaGo, which is based on a pipeline of classical machine learning approaches. And at the beginning of this pipeline, we start with a human data set, a data set of positions, and for each position we have a label that says what the move was that was chosen by a strong human player. And what we do is we train our policy network, first of all, by supervised learning to classify that human move. To say in this position, we would like our network to predict the same move that that human played in that particular position. And once we have this policy network P, we're able to play games against itself using the policy network, for now without any search at all. So it plays games against itself, the policy network picking a move for both players, for both black and white, all the way through the game until the end of the game, at which point we have a winner of that game. And what we do is we then train our value network, this value network which we indicate by V here, this pink V, We train the value network by reinforcement learning to predict the winner of the game from each one of those positions. So from every position, we would ask our value network to correctly predict which of those two players, black or white, will win when the policy network plays against itself. So that was the original AlphaGo training pipeline. And the main idea of AlphaGo is to really use the policy network and value network to make search tractable. So again, we see here a kind of cartoon representation of this enormous search space that we have in the game of Go. Where here we're just looking at a cartoon where we have just two different moves that are possible from each of these small states. But in reality, there would be several hundred moves, and this tree would be vast. And so what can we do? How can we make this search tree more tractable using our neural networks? Well, the first idea is to use the policy network to reduce the breadth of the search tree. So recall that the policy network suggests moves to make in each position. And so we can actually reduce the breadth of this search by only considering moves that are recommended by the policy network. So instead of searching 200 or so moves from each state, we might consider just a handful and just kind of expand that handful of moves in the search tree to dramatically narrow the set of possible sequences that we need to consider. The second idea is to use the value network to actually reduce the depth of the search. So the value network predicts the winner of the game from any position. And so that means that we can actually use the value network to replace any subtree of our search tree with a single number. So that means that we can actually, instead of searching all the way to the end of the game, we can truncate our sequence at a leaf node, and we can replace the subtree that we would have had to search systematically all the way to the end of the game. We can replace that whole search tree with a single evaluation of our neural network. And this dramatically reduces the size of the search space that we need to consider. So in practice, we actually use a more sophisticated search algorithm than that cartoon suggested, which is based on Monte-Carlo tree search. So I'm just going to briefly illustrate how this works. If you'd like more details, you can read the papers and so forth. But the algorithm proceeds in 3 stages. So in the first stage, the algorithm traverses the tree from root to leaf. Picking at each node, it picks a child based on a kind of upper confidence rule to decide which action it should select. And so this rule actually selects actions that have been evaluated most highly in past simulations. That's this Q value from each node. And it also prefers to choose actions that the policy network likes. That's this U term. The U term kind of is a bonus term that includes what the policy network thinks of the move. In the second stage, once we've actually traversed this simulation down to a leaf node, we expand the leaf node and evaluate this new node with both the policy and the value networks. And finally, in the third stage, we back up the evaluation. So whatever this evaluation was, according to the value network, we back that up through the search tree so that at every node, we maintain the mean evaluation from each of those edges. So each Q value there is basically storing the mean evaluation that it's seen from that point onwards in the search. And this process of Monte-Carlo tree search, can very effectively expand a very large search tree by just considering the most important parts of that search tree get expanded, and it systematically kind of gets deeper and deeper and deeper, but in a very selective fashion, so it only considers the important parts of the search tree. So we applied AlphaGo in a match against the winner of 18 world titles, Lee Sedol. So he's widely considered to be the greatest player of recent decades. And this match was played between AlphaGo and Lee Sedol in 2016. And AlphaGo actually won the match by 4 games to 1. But that one game that we lost actually highlighted some of the deficiencies of AlphaGo. So in particular, we found that in some kinds of position, AlphaGo can systematically misevaluate, misunderstand those positions. We used to call these delusions. It would enter into a type of position where it failed to understand what was going on there, and that kind of misunderstanding could persist for many different positions throughout the game. So it could persist for 10 or 20 or 30 moves. And we really wanted to understand this, and this led to us actually progressing further to try and understand and progress AlphaGo towards something which could play much more strongly without exhibiting these kinds of weaknesses. And this led to a subsequent version of AlphaGo, which we called AlphaGo Master. So for AlphaGo Master, we trained new policy networks and new value networks using much deeper state-of-the-art residual networks and using many more iterations of reinforcement learning with more precise kinds of evaluation. And so AlphaGo Master, we played earlier this year against the world's ranked #1 player, Ke Jie, and we won 3 games to 0. But perhaps more encouragingly than that still, we played online in a series of 60 matches, 60 games against the top-ranked human players in the world, and we won by 60 games to 0. So I think what this shows is that principled reinforcement learning combined with principled deep learning can address these kinds of systematic delusion that we saw. That just by sticking to our principles and doing things just further and better, we can actually start to address things which people believed at the time would require new kinds of research. But really, all the principles are already there. We just needed to do it very well. So I'm now going to move on to our more recent work, which we call AlphaGo Zero. So the goal of AlphaGo Zero is to take every form of human knowledge that went into the previous version of AlphaGo and remove it from the training process, except for the rules themselves. So the idea of AlphaGo Zero is really to learn to play the game of Go tabula rasa, starting from first principles, and really understanding and discovering knowledge about the game completely for itself, without any human actually having to tell it the kind of things to do, or any human data to guide it, or anything else like that. And so the differences between AlphaGo Zero and the previous AlphaGo are essentially listed on this slide. The first and most important is that it uses no human data whatsoever. So it learns solely by self-play, by playing games against itself, and training by reinforcement learning, starting from completely random games. So in other words, we initialize our neural network to random weights, and it plays games against itself starting with those random weights, so it knows nothing about the game, and everything else is discovered from there onwards. The second difference is that AlphaGo Zero uses absolutely no handcrafted features. There's nothing in there beyond the raw board. So all it sees when it takes, the only thing that the neural network sees and receives as an input is actually a representation of the raw board. So it just has a plane saying, whether there's black stones in this position, and plane saying whether there's white stones in this position. And that's it. That's all it sees. But there are some additional differences. One of the most notable ones is that we actually unified the policy network and value network into a single neural network, again, based on a state-of-the-art residual network. And this actually helped to regularize the network and make it much more robust against the kind of overfitting which it's possible to see if you just have a value network trained by itself, for example. In addition, AlphaGo Zero actually uses a simpler search. So in previous Monte-Carlo tree searches, and to an extent the previous version of AlphaGo, there was actually these randomized Monte-Carlo rollouts. In other words, when you reached a leaf node, it used to do something where it would run a random game all the way to the end, and then evaluate that node based on how well that random rollout performed. And so you'd be in this situation where if random games tended to win more often, you would start to believe that was a very effective position. So actually, in AlphaGo Zero, we removed those rollouts altogether. We really wanted to have the simplest possible approach with a minimal level of knowledge. And so we removed those, and we only used the neural network to evaluate positions. And maybe one of the principles which we're after in AlphaGo Zero is this idea that by doing less, by actually removing complexity from the algorithm, it enables us to actually become more general. We want to have something which can not only be applied to the game of Go, which after all is just one domain. We want to get at the heart of what it means to really learn. We want to have something which can really learn from first principles, potentially in any domain. Of course, the game of Go is a first step, but it's a challenging first step. And if we can understand how to learn from first principles to discover knowledge and reach the highest levels of human capabilities there, maybe this is something which has more capability to transfer to other domains. So this is the goal: less complexity, more generality. So I'm now going to describe the algorithm which we actually used in AlphaGo Zero. So the main idea is that AlphaGo actually becomes its own teacher. So in a sense, what we want is we want to have the highest quality data to train our algorithm on. We want to train our neural networks from really, really high quality data, really high quality move selections and really high quality outcomes. And the best possible data that we can get our hands on actually comes from playing AlphaGo against itself. So the idea is really to do the following: that from each position, we execute a Monte-Carlo tree search using our current neural network, so this policy and value combined network, P and V there. That kind of guides this tree search to suggest ultimately at the end of the tree search a move is suggested. We play that move, we run another search, play another move, and so forth, all the way until we've completed a game. When that game is completed, it's scored and we determine the winner of the game. The next stage is we train a new neural network. So the policy part of the network is updated to predict the move that was actually played by AlphaGo itself in each position. So this new policy network, P prime, from each of these positions that were actually reached in this game, we want to basically get the neural network to predict the move that was actually played. We want the raw neural network to directly predict the action that was chosen by an entire MCTS. So in other words, we want to kind of compress everything which was achieved using look-ahead into the neural network so that it can distill all of that knowledge into its direct behavior. At the same time, we also train a new value network. So this is the value part of our neural network, and that, at the same time, gets trained to predict the winner of this game. So at the end of this, again, we're looking at this game that was played by self-play, and from each of the positions that was reached during this game, we would like to predict the winner of that game. So, and we simply train our network to predict both the winner and also the move that was played. So we have this joint training rule with these just 2 terms to it and a simple regularization. And that's it. That's the whole of AlphaGo Zero. And finally, once we have this, we iterate the procedure. So we now have a new policy and value network, and this could be used in the next iteration of AlphaGo Zero. And the key idea is that each time we iterate this process, we end up with an even stronger player, and because we have a stronger player, it generates even higher quality data. So each time we improve the quality of the search, it means that we actually end up with outcomes which are more indicative of optimal play. And then we can train our new generation of neural networks based on those higher quality searches, this higher quality move selection, and the higher quality outcomes. And this process can be repeated almost indefinitely, and then tends to lead to just stronger and stronger play. So if we relate this to what's been done before in reinforcement learning, this relates to a very well-known idea in reinforcement learning, which is the classic policy iteration algorithm. The twist here is that we actually incorporate AlphaGo search inside the policy iteration. So we call this search-based policy iteration. And the idea is that in a policy iteration, we interleave 2 phases. There's policy improvement, where the action selection is somehow made stronger, and then there's a policy evaluation, where the quality of these selected actions is evaluated. And the whole idea of policy iteration is that if you alternate between these 2 stages, you end up getting a stronger and stronger policy, which ends up eventually ideally approximating the optimal policy. And so what we do in AlphaGo Zero is we actually use search-based policy improvement. So the idea is that instead of, say, using a greedy policy improvement, as it's traditionally done in RL, we use the whole of our search as the policy improvement. So in other words, we start off with our raw neural network, which picks an action, and we massively improve that policy in one shot by running a search. And the action which is picked by the search is typically much, much stronger than the action which was selected by the raw neural network, because it's incorporated all of this look-ahead. In addition, we incorporate search into the policy evaluation. So we use search-based policy evaluation, and what this means is that we play our self-play games with AlphaGo actually running its search at every step. And so what this does is it means that we're actually evaluating the improved policy. We're not evaluating the raw neural network, we're evaluating the improved policy. And this gives us very, very high quality outcomes, which enables us to really, in every step, have very high quality data that leads to very precise training signals for our neural networks. So this all relates to prior work and also recent work that's been done elsewhere in RL, starting with Michail Lagoudakis in 2003, who had a paper on classification-based reinforcement learning. But in all of this other work, what's happened is there's been a focus on the search-based policy improvement in some sense, but there hasn't been previously this idea of search-based policy evaluation, and that turned out to be absolutely critical in AlphaGo Zero. That this was the step. If you had to pick out the one step which led to thousands of ELO improvement in its performance, it's that second one. But the overall algorithm is very effective and seems to be rather robust and reliable, as we'll see. So if we look here at a learning curve, this is a learning curve starting from 0 knowledge and running for 40 days. So time here is the x-axis. It's actually, we measure in time. This corresponds, if you want to know, to around 30 million actual games. But actually, for us as developers, time is the thing which matters, because this is what determines how many iterations of the algorithm we can run. And as developers and researchers, that's the thing you ultimately care about. And on the y-axis, we have the ELO rating. ELO ratings are the commonest form of evaluation in games like chess and Go and so forth. So what we see here is that it started off playing completely randomly at the start of this timeline. So it really had completely randomized initial weights. But after 3 days, it already surpassed the version of AlphaGo, which we call AlphaGo Lee, that defeated Lee Sedol in 2016. So that happened in just 72 hours. After 21 days, we saw that AlphaGo Zero surpassed AlphaGo Master, this previous best version that we'd had that had defeated human players by 60 games to 0. And eventually, after 40 days, we ended up with our strongest version of AlphaGo Zero, although it was still continuing to improve, so potentially it could have been left to climb even more. So if we actually try to evaluate AlphaGo and look at it and try and quantify what these improvements really mean, we started out with some kind of previous state of the art on this ELO scale, which were previous programs. And one way to understand this, which is maybe more understandable to us in the audience here, is by instead of looking at ELO ratings, we can look at the number of stones of difference between programs. So this roughly says how many extra moves one program can give another and still win. And so between the original version of AlphaGo, which we published in our first Nature article, and the previous state of the art was around a 4-stone difference. And this is the version that defeated the European champion by 5 games to 0. We subsequently developed the version AlphaGo Lee that defeated the world champion Lee Sedol by 4 games to 1. And that was around 3 stones stronger than the previous version. Although you have to take all of these stone evaluations with a pinch of salt, because it turns out that we do very, very well at defeating weaker versions of ourselves, because we've essentially trained by self-play, and therefore we are better at beating previous versions of ourselves than we would necessarily be at beating some held-out other program. And from there, we went on to develop AlphaGo Master, which was another 3 stones stronger, and this was the version that beat the top professionals 60 games to 0. And finally, we ended up with something around 5,000 ELO, which was the AlphaGo Zero. And this was the one which was trained completely from first principles. So all of the knowledge had been removed. So one of the nice things about AlphaGo, and AlphaGo Zero in particular, is that it can actually learn to discover human knowledge for itself. So it starts from random weights, which means that everything it learns for a reason. It learns because it finds some pattern which it has discovered is important in games of self-play. And so over time, it really starts to understand the game, and we can really think of this as some form of understanding. It's developed the intuitions that are important for it to be able to evaluate and play this game effectively. And so in particular, we analyzed the actual opening patterns. These are called joseki in the game of Go. These are like corner sequences that strong human players use to play out positions in different situations. And all of these known opening patterns, or joseki, were discovered as training proceeded. So it started from nothing, but as training proceeded, this is like a timeline we see here, starting from 0 hours and going up to 72 hours. We see that it started to pick out really well-known joseki that humans play. But what was interesting is that some of them then get discarded. That it starts to play them, but after a while it discovers that actually it's found some better variation, and it discards them and prefers new patterns and new ideas which actually human players didn't necessarily know about. And so this is now adding to the knowledge base and enabling humans to play in new ways. So finally, I'd like to talk about the most recent work. So this was just published a couple of days ago. This is something we called AlphaZero. And really, I think this comes from the idea that an algorithm, it can't really be claimed to be general unless it's applied to multiple domains. So of course, the motivation for AlphaGo Zero was to be general by using less knowledge, but we really wanted to demonstrate that fact. And so we wanted to apply the same algorithm to 3 different games. And so we applied it not just to Go, but to the games of chess and Shogi. So the game of chess has a lower complexity than Go, but it's still a really considerable challenge. There's around 10 to the 48 states. However, chess is interesting to us for very different reasons, actually, to Go. So computer chess is actually the most studied, arguably the most studied domain in the history of artificial intelligence. So it turns out that actually the pioneers of computer science, people like Babbage, Turing, Shannon, and von Neumann, were absolutely fascinated by computer chess and developed, sometimes just on paper, the very first algorithms to play chess with a computer. And subsequently, chess became the Drosophila of artificial intelligence, the kind of the platform that everyone used, the fruit fly, in other words, that everyone used to conduct their experiments on for decades of research. And actually, this research developed enormous progress, and huge numbers of ideas were thrown in, and programs got stronger and stronger and stronger, culminating in these highly specialized systems, which were very successful in chess. And ultimately, the program Deep Blue from IBM defeated Garry Kasparov in 1997. But in the 20 years since then, the state of the art continued to progress to a level where they're now indisputably human. I think the top programs are something like 600 ELO stronger than Deep Blue was. So this gives us a really fantastic case study of a domain where the expertise of humans has been leveraged and specialized to really produce the best that can possibly be done in that one domain. So we also looked at the game of Shogi. So this is Japanese chess. And Shogi is interesting to us because it's both harder than chess in terms of computation. So it uses a larger board, but also it has a much larger and more interesting action space. And that's because in the game of Japanese chess, Shogi, when you capture a piece, it actually kind of flips around and becomes one of your own pieces. And then on your move, you can place it down at any position on the board. And this really blows up the action space and leads to enormously complicated tactical sequences. And what this means is that actually in the game of Shogi, the strongest computers, despite a lot of effort, have actually only recently achieved human world champion level. And so it becomes an interesting case study for us. And so both of these cases, for chess and Shogi, the state-of-the-art engines are based on alpha-beta search. So alpha-beta search is a form of minimax search where the minimax optimal solution is found by a kind of search tree. And that alpha-beta search has been augmented by enormous amounts of knowledge. So in particular, what goes into it typically is a handcrafted evaluation function that's been tuned by human grandmasters over many, many years. The whole history of computer chess has led to these grandmasters creating these very complicated and specific features which enable chess programs to effectively and efficiently evaluate positions. And in addition, they have a huge number of search extensions that are highly optimized to the particular game of chess. So I think it's useful to actually make this concrete, so we can actually start to dissect one of the top programs. So I'm going to look at the program Stockfish, which was the 2016 World Computer Chess Champion. And this is a really beautifully engineered program with a vast array of specialized components in it. And what I'm going to put up is a list here in which every item represents a major component of Stockfish. And most of these components you would also find in other top chess programs, or you'd find equivalent components. And each one of these items you can think of as corresponding to potentially years of research in the computer chess community to get this idea or this particular search extension right. And the majority of them, some of them are very general purpose, but the majority of them actually use a lot of specialized knowledge which is specific to the game of chess. And so we would like to replace this with a system which learns for itself and which can therefore be applied to other domains. And so if we look at the equivalent anatomy of AlphaZero, we can essentially remove every single one of those components and replace them with principled ideas based on self-play reinforcement learning and self-play Monte-Carlo search only. And literally there are none of these in there. There's no transposition table, there's no opening book, no endgame table bases, no extensions. So then the question is, how well can an approach which is really very pure actually do compared to these traditional approaches which have been optimized for decades? Well, I think to answer that question, we really need to understand some of the properties of chess and shogi compared to the game of Go. Because one of the reasons we wanted to study this is to see whether the kind of success we saw in Go was specific to Go, or whether it would actually generalize to a game with very different properties. So for example, chess, unlike Go, doesn't have perfect translational invariance. That's because you've got pawns which can move in different ways at different parts of the board. They promote at their 8th rank and they move 2 steps from the 2nd rank and things like this. They don't have this kind of perfect locality that you have in the game of Go. So in the game of Go, the rules are very local. They're defined in terms of the adjacencies of the stones to the next stone, whereas the rules of chess are defined in terms of like queen moves, which can jump you from one side of the board to the other. And so these first 2 properties may be things which make training more amenable to convolutional neural networks, for example. The third point is symmetry, that AlphaGo actually exploited symmetry, the original version, because the game of Go is perfectly symmetric with this 8-fold dihedral symmetry, whereas chess actually is not symmetric because there are symmetry breaking things in it. There's pawns always move forward, and there are castling rules which are different on both sides of the board. So we actually threw out all of the symmetry augmentations that we used in AlphaGo, and we wanted this to be as general as possible. The action space is also more interesting in chess and shogi because it has these kind of compound actions where you pick up a piece and then you move it somewhere else. And so it's not just like pointing to one particular location on the board, there's this compound structure to it. And finally, in the game of Go, there are no draws. And this means that you actually have a binary outcome, meaning that the value function actually has this very nice interpretation as a probability of winning. And it may be that led to particularly nice dynamics for the game, And so for chess, we actually have draws. In fact, there are so many draws that they tend to dominate in high-level chess play, particularly with computers, and it's believed that the optimal outcome of chess is a draw. And so we really needed to evaluate something which took account of all possible outcomes, and we chose to use the expected value as for a standard value function, with a -1 for a loss, +1 for a win, and 0 for a draw. And so the question is whether we would need to do anything different for all of these properties. But despite all of these differences, we applied exactly the same algorithm as I've described earlier in the talk, using the same network architecture and the same settings for all games, for Go, chess, and Shogi. So if we look at how it does, this is the learning curves for the 3 games. So first of all, again, we see that this x-axis represents a kind of measure of time. This is now the number of training steps. So this is the thousands of mini batches which get updated by the training algorithm. So this is 100,000 training mini batches, 200,000 mini batches, and so forth. And the y-axis is again an ELO rating, which should be interpreted differently for each of these games. For example, in Shogi and Go, the scale seems to be more elongated, whereas in chess it gets more compressed because of the prevalence of draws. And so we see that in chess, we actually, starting from scratch and starting from random, within just 4 hours, around 200,000 steps, outperformed this previous world champion, Stockfish. In the game of Shogi, it took just around 100,000 steps, or 2 hours, to surpass the world champion in the Computer Shogi Association. And in the game of Go, as a control, we compared to the previous version of AlphaZero, and actually, despite not using symmetries, we actually learned to outperform the previous version of AlphaZero, and not only that, but we defeated the AlphaGo Lee, the version that defeated Lee Sedol, in just around just a few 100,000 steps here, so around 8 hours of training. So we also played, once these were fully trained, we played matches against the previous state of the art in chess, Shogi, and Go. And so what you see here is that in a 100-game match against the world champion Stockfish, we didn't lose a single game. When we played against the current world champion in Shogi, we won around 90% of the games. And finally, we were able to defeat the previous version of AlphaGo Zero using equivalent network architecture. So we also wanted to look at the scalability of AlphaZero's Monte-Carlo tree search. And we really wanted to compare this to the alpha-beta search engines that have been used in previous programs. And this is interesting because alpha-beta search has dominated in these domains for 40 years now. And there have been many studies that suggested that actually MCTS or any other algorithm than alpha-beta could not be competitive. And yet what we see here is that not only did we outperform these other programs, but that MCTS actually scaled up more effectively than alpha-beta. So the more thinking time we give the program, the more it starts to outperform Stockfish in chess and Elmo in Go. And not only that, but it actually used around 1,000 times fewer evaluations per second than these programs. So Stockfish evaluates around 70 million positions per second, whereas AlphaZero is picking out just something like 80,000 positions per second. And this is interesting because actually when Shannon was looking into computer chess, he proposed that there are actually 2 ways to consider planning. He called them type A and type B. He said that type A algorithms would essentially be doing brute force search, where they'd be systematically evaluating every kind of position you can come across. And that type B algorithms would be using a more brain-like system, where they would actually be carefully deciding which of these positions should be expanded next, based on an understanding of what's going on in the position. And it turned out that for decades, these type A, these kind of more systematic searches have dominated. But it looks like what's happening here is perhaps something more like that original spirit of type B, where despite evaluating orders of magnitude fewer positions, if you actually evaluate those in the right way and you're very careful about what you evaluate, you can actually get better performance and better scalability. So we think that one reason why MCTS is so effective compared to alpha-beta when you start to use these approximate function approximators like neural networks is that like a neural network inevitably is going to have some kind of approximation error in it. And what happens when you do an alpha-beta search? So alpha-beta search is a kind of mini-max search. So you can think of it as like a great big glorified max operator, although it's alternating with mins as well. And what happens is that will pick out the biggest errors in your function approximator and propagate them right to the root. Whereas MCTS is actually averaging over the evaluations that you have. And so this actually tends to cancel out these errors that you have in your search. And we're just speculating at this point, but this may be one of the reasons why MCTS can be so effective when it's combined with deep function approximators. So as in the game of Go, we see that AlphaZero also discovered human chess knowledge for itself. So what we did was we actually picked out the 12 most common human openings that were played, all the openings that were played more than 100,000 times in an online database. I've shown the first set here. And we checked out how often AlphaZero played these games during self-play. And that's this plot that you see here. It's the frequency by which it was played during games of self-play. And what we see is that AlphaZero played most of these variations extensively, but it ended up dismissing some of these variations, like the French defense, later on as it discovered and started to prefer different variations. In addition, we also tried playing a match against Stockfish from each one of these openings to make sure that we could actually perform robustly, and we hadn't just discovered like one exploit against Stockfish. And we actually beat Stockfish robustly from all of these 12 positions. So I just wanted to conclude by just talking about what happens when we move beyond games. So of course the idea of AlphaZero is actually to be able to take us beyond Go and into the realm of general purpose reinforcement learning. Now, at the moment, it's still early steps, and I would of course hesitate to say that, that the real world is anything like the game of Go or the game of chess. But nevertheless, one thing which we're very interested in is trying to progress these methods to general purpose deep reinforcement learning ideas. And so what we've been looking at Deepmind in general, and not necessarily using the kind of planning methods that we saw in AlphaZero, but using a whole host, a whole array of different approaches, are these deep reinforcement learning algorithms. So for example, here is one of the state-of-the-art algorithms we have, which is called Unreal, and which is based on a much more model-free approach, which is learning to play in these Deepmind lab domains by learning about a whole host of different targets. And I'll actually be talking about this particular example in a couple of days at the hierarchical reinforcement learning workshop. But what we'd like to do is keep progressing beyond these games. And the key idea, and the thing which I think I want to emphasize from this talk, more than anything else, is that the more we take out specialized knowledge, the more we enable our algorithms to be general purpose, and the more we can hope and start to believe that they will actually transfer into something which will be helpful and successful in domains beyond the ones for which it was designed and tested. And I think there's a lesson there, which is, every time you specialize something, you actually hurt your generalization ability. So that's really it. I just wanted to conclude by asking for questions, and I'll put this online, but there's some links if you're interested in any more resources and games and so forth. Thank you very much. Okay. So there are microphones scattered in the aisles. If you'd like to come up and ask questions, we can have a few now.
Hello. Thank you for the presentation. It was wonderful. One of the things that I had seen that has been worked on in chess was that even though computers were on superhuman level, but when the analysis that computer was doing was given to the human plus computer could outperform the computer by itself. So I wonder if you have done any of that sort of analysis to see if, given this type of reinforcement learning solution that we have, humans still have a new perspective, a way that the human intelligence works that could add to the solution, and it could actually outperform AlphaZero itself.
So that's a great question. I mean, I should say for chess in particular, we literally just put up these results a couple of days ago, so they're brand new, and we haven't had really a chance to perform these kind of extensive investigations. I think the question of these centaur programs, which combine human and a machine together, is very interesting. Maybe I could just, I don't want to speculate on what would happen because I genuinely don't know. But I think maybe one comment would be, which I can pass on, is the reaction of the chess community to the style of AlphaZero and the way it plays chess. And the reaction has been that it plays in a much more human way than previous chess programs. So it actually plays in a way where it tends to play quite aggressively, freely, this kind of open style which humans tend to favor, but of course with the additional precision of computer abilities. And I think in addition to that, it's found this new style which hadn't been seen before, where it can do things like be quite free about its ideas about when material is worthwhile. So it will, for example, give up a knight, not because it sees that it can win back that material within its search tree, but because it's understood within its deep understanding of what's going on in its position that it can exert some advantage over the opponent that's worth more than a knight. And we have an example in the games that we put out where it takes more than 50 moves before it wins back the material from this knight sacrifice, for example. But yeah, I think interesting question. Thank you. Okay, 2 more questions, apparently.
So you mentioned that the only human knowledge that you embedded into the AlphaGo Zero was the rules of the game. So I guess I have a more this like basic question. What are the output moves? How are the output moves represented? And then how do you prevent the network from making an invalid move?
Okay, so so first of all, yeah, I didn't have a chance to explain, but we have to use, when I say we use the rules of the game includes some basic encoding of those rules into the inputs and some basic decoding of the action from back into actually playing a move in the game. So what we do specifically in the game of chess is that we have, we tried a couple of things actually. We tried a flat encoding, which also worked, by the way, where you just have a flat vector distribution. And we also had a spatial representation, which had basically where we used the piece that you pick up was spatially encoded, and the place that you put it down was the particular plane that you use. So is that knowledge? Well, it's a way to encode the rules. You need some way to interface between what the machine does and what's going on in the game. And so I think, to me, that becomes part of what the rule definitions are. I think the fact that it also works with a flat representation suggests that we're not too sensitive to that, and that's something which we substitute between the different games. For the legal moves, yeah, that's also included in knowledge of the rules, so we do exclude illegal moves, and that's helpful in chess because you have a very large action space. Yeah, so a question from over here.
Yep, nice talk. I would like to know some more about your experiments. The curves you show don't have error bars. Is it because the error bars are too small to see, or are we seeing just one run chosen at random?
So these runs are very expensive. So this is just one run per game. I mean, this is using a large number of TPUs on Google Compute.
So you've never run 2 experiments on this. You've run only 1 experiment in the history of your project.
So we are reporting a single experiment here. We have ourselves run multiple experiments, and it's very reproducible. So we get the same results essentially every time.
Thank you.
Yeah. Okay. Thank you very much.